So let's continue with our playlist. But before that, hey, welcome back to the channel. I hope you guys are doing extremely well. So the problem that we will be solving today is detecting a loop in a given linked list. So what is the problem stating? It is stating that you'll be given the head of a linked list. Yes, you'll be given the head of a linked list and you'll have to return me true if there is a loop in that given linked list. So what is the definition of a loop when it comes to linked list? And the definition is if there exists a minimum of one node where you start and you reach back, then we can say that the linked list has a loop. Let me explain you. If I start at 4 and I move ahead, I'll be reaching back to 4. So I'm sure that there is a minimum of one node where I can start and reach back. And if there does exist a minimum of one node, I can say that there is a loop, and in that case, I'll be returning true. Got it? Now over here, there are multiple nodes, 3, 4, 5, 6, 7, 8, 9. If you start from any of them, you will reach back. But if you start from one, you will never reach back one. So that is why I'm saying a minimum of one node is required. What if this problem comes up in an interview? We will be starting off with the extreme naive solution. And what will be that? What are we looking for? We are saying that in case there is a minimum of one node where you start and you reach back, that means it is visited more than once. I'll have to remember somehow that I've seen it previously, because when I'm traversing, I need to remember that I had seen 5 previously, and that is when I reach back 5, I'll know, hey, I did see this node previously, and that is what will tell me that, hey, there is one node minimum which has been seen twice, and if it has been seen twice, it means that you're on a loop. So which data structure to use to remember these things? Yeah, you're correct. We'll be using the concept of hashing. So what we will do is, again, we will not tamper head. We will take temporary and we will take a map data structure. So let's take a map data structure. And what we will do is, this map data structure will be of the type node. Node will be the key and integer or boolean. So basically the node will be the key and integer 1 or boolean true will tell me if I saw that, or integer 0 will tell me that I haven't seen it. So what we do is, we start with the temporary, which is the node 1. So we keep the node 1 and we say I have seen it. Perfect. Let's move the temporary to the next. Goes to 2. I'll store 2 and say I've seen it. Goes to 3. I'll store 3 and I'll move ahead. Goes to 4. I'll store 4 and move ahead. Goes to 5. Remember, you store the entire node, not the values. Because it might happen the values might repeat in the node. So do not store the values. Store the entire node, entire object in itself. Okay. So 5 stored. Let's move to 6. 6 stored. Let's move to 7. 7 stored. Let's move to 8. 8 stored. Let's move to 9. 9 stored. And the moment we move back to 3, what you do always is, before storing it, just a small step. Just introduce a small step to check if this 3 that you're currently at, is it in the map? And you can see that there's a node with 3. There's a node, exact same node. I'm not considering the values. I'll be comparing the object. Is it the same memory location? He says, yes, it is the same memory location. It is pointing to the same memory location. If it is, I can say that I've encountered a loop and I will stop. So this is what we can do. Like, we can simply use hashing. So if I have to write down the code, can I say I'll be requiring a map data structure which will be storing the node in Java, node star in C++, int, and a map. Again, I'll be writing the pseudo code. You can find out the C++, Java, Python, JavaScript codes in the description below. So this is how we start off with. Right after that, what is the next step? I know I need a temporary which points to head, because usually we do not tamper head. So we will take the head to temporary and we will start moving. We will say temporary not null. Perfect. and we need to insert it into the head. But I did tell you, before inserting, have a check. So you say, hey map, find, or whatever is your function, depending on whatever language you're using, just look at the map. So you can say look in the map. So it can be find, it can be search, depending on your language. Find this particular node temporary. If you can find it, it means it is there, and you say, hey, return true. Return true means it's a loop. Or else you say map, can you put, in Java it is put, in C++ you can straight away say temporary equal to 1. In Java you can write mpp.put, and you can put this value temp, comma 1. That is your choice, how you want to do. Once you put it into the map, let's traverse to the next, which is temp equal to temp next. And understand one thing, why have I written not equal to null? Because if I had a linear data structure, temp would have started from here, gone here, stored everything into the map, and then at the end it would have ended at null. The moment it would have ended at null, the while will be done, and I can straight away return false, stating there is no loop. Got it? That is why it's very important to have a check for null, because it might not happen, like there might not be a loop. So what about the time complexity? Can I say I'm traversing the entire linked list? I am. And at the same time, I have a couple of map operations. If you carefully see, one is inserting to the map, the other is checking in the map. So there are two map operations. So depending on if your map takes logarithmic, right, depending on whatever your map takes, it will be 2 into log of n, or 2 into 1 if your map is a big of 1 time complexity. I've already discussed the time complexity of maps in the hashing lecture. Please go back and watch it, you'll understand this. So depending on your language, your map's time complexity, you can determine that. And what about the space complexity? I'm storing all the nodes in the map, so big O of n, because no matter what you do, you will end up storing all the nodes. That is something which will happen for sure. So this is the time complexity and the space complexity. This is where the interviewer will not be happy with the extra space that you're using, and he'll ask you to optimize it. So the optimal approach will be using the tortoise and the hare algorithm. In case you're not aware of this, please go back and watch out the lecture, finding the middle of the linked list, because that is where I've discussed this algorithm, the slow and the fast pointer algorithm, which is basically the tortoise and the hare algorithm. So in this particular algorithm, we take couple of pointers, slow and the fast pointer. Slow will be moving by 1 step. The fast pointer will be moving by 2 steps, and they will be moving simultaneously together. So what we do is, we're given the head of the linked list, right? So we will take 2 pointers, slow and the fast pointer, and we will try to move them simultaneously, one by one, the other by 2. So let's start slow and fast. Let's move them together. Slow, as we said, by 1, fast, as we said, by 2. That's the first step. 1, 2, done. Let's do the next step. Again, slow and fast will move by 1 and 1. So slow will reach here and the fast will reach here. So this is where they reach. I'll be raising this so that it has more clarity. In the next step, again they'll be moving 2 steps. So the fast pointer will reach here and the slow pointer will reach here. So this is how it moves step by step. In the next step, again they'll be moving 2 steps. So the fast pointer will reach here and the slow pointer will reach here. So this is how it will look like. Perfect. In the next step, again move them by 1 and 2. So slow will be here and the fast pointer will be somewhere here, because 2 steps, it doesn't go like it does. It will not go in this direction. It has to go in this direction. So this is what it will look like after the step. Let's do one more step. Slow and fast. Slow will go, sorry, my bad. Slow will be over here and the fast pointer will move over here. Perfect. This is how they will look like. And in the next step, the slow will move over here and the fast pointer will move over here. And this is when they stop. And this is when they stop. And if they're meeting, I repeat, if they're meeting, you will be like, yes, there is a loop. So after this step, you can see that the slow and the fast pointer are standing at the same node. if it happens to stand at the same node at any junction, you can definitely say that there was a loop. There was a loop. That is why they are standing at the same node, and you will be returning true. As of now, just remember this. You might be thinking, why? What if they cross over? What if? How are we so sure that they will be colliding at a single node? What if they cross over? I'll be telling you the entire intuition. Do not worry about that. Please stay with me till the end. So before I move on to the intuition, what if we have a linear linked list with odd number of nodes? Over here n is odd. What if we have a linear linked list with even number of nodes? In that case, what will be our stop condition? Because in this case we'll be just rotating around. There is no stop condition. The stop condition is whenever we meet slow, like whenever the slow and the fast pointer meets, that is the stop condition. What about linear linked list without loops? What is the stop condition? We did it while doing the middle of the linked list, but I'll be doing it again. Slow and the fast stands at the head. Simultaneously, slow and the fast pointer will take 1 and 2 steps. In the next, the slow takes 1 step, the fast pointer takes 2 steps. Next, you do not do anything. You see that right after this there is null. That means you're standing at the last node. Remember, if at any moment you stand at the last node, you stop then and there. Which means if your fast dot next is not null, then only you will move. Because if it is null, it means it is the last node. And you know, in case of loops, there can never be a last node. There can never be a last node, right? Let's check out the case for the other one. So what I'll do is I'll quickly erase this. I'll keep the slow and the fast pointer over here. Let's again try to do the same thing. Slow and the fast. Slow moves by 1. The fast pointer moves by 2. Perfect. Again, let's do it. The slow moves by 1. The fast pointer moves by 2. Perfect. Let's again do it. The slow moves by 1 and the fast pointer moves by 2. This moment it reaches null. So please make sure that the fast pointer never reaches null as well, because if it reaches, that means it is a linear data structure, linear linked list, and you need to stop. Got it? So what you'll do is you'll initially have slow equal to head. You'll also have the fast equal to head. And let's do this thing. What are you waiting for? Slow equal to slow, next. Fast equal to fast, next. We know if at any moment the slow is standing with the fast, it means there is a loop, so you'll return true. In case the while loop returns false, it means it's a linear data structure, and if it means that, I will be returning false because it will never have a loop. Otherwise, it will never reach the last node or the null. So, it will be returning false. So, this is how the code will look like for the optimal approach. And you might be thinking, we have understood the code, we have understood the algorithm. But what is the intuition? Because how are we so sure that they will be colliding at a certain node? Because what if they cross over? They might cross over, right? And they might never collide. So how are we proving that they will collide? Let's understand that. So what did we do? We took a slow pointer and we placed it at the head. We took a fast pointer and we placed it at the head. And after that, simultaneously, we moved slow by 1 and the fast by 2. Correct? So let's move the slow by 1 and the fast pointer by 2 steps. That was the first step, right? What was the next? We took the slow and we moved it by 1, and we took the fast pointer and moved it by 2 steps. So let's move it. We stop here, and I will be proving you why they will collide and why they will never overlap. They will collide if there is a loop. Slow is standing here, the fast pointer is standing here. Can I say the distance between fast and slow, not slow and fast and slow, how much is that? That's 1, 2, 3, 4, 5. Can I say that the distance between them is d? Let's assume the distance d. And in this example, it is 5. In this example, it is 5. And overall, we can assume it is d. D can be any number. It can be prime. It can be odd. It can be even. It can be any number. Now tell me one thing. After this process, what will happen? Let's erase this. After this process, what will happen? The fast pointer will again move by 2 step, and the slow pointer will move by 1 step. Can I see this? I can, and I'll erase it. Now if I ask you, what is the distance between the fast and the slow? Not slow and fast and the slow. You'll be like, the distance is 1, 2, 3, 4. D is 4. What was the reduction in distance? 1. The reduction in distance was 1. Okay. Why did that happen? Because the slow is moving by 1 and the fast is moving by 2. And you had a distance between the fast and the slow as d. That was the distance. So if the fast is moving towards slow by 2, and the slow is moving away by 1, what is the net reduction? What is the net reduction that they will have? The net reduction will boil down to d minus 1. Because fast is moving 2. Towards, whereas slow is going farther by 1. So the overall reduction will be 1. Fast will be closer by 1. What will be the next? 3. Yes. What will be the next? 2. After every movement, the distance between them. Next 1. And there will be a point it will be 0. So one thing I have proved is, no matter how far is fast from slow, the d can be any number, odd, even, anything. It can be anything. But d will reduce to d minus 1 to d minus 2, and it will end up reducing to 0 because we are reducing it by 1. It's 1. And you know, d is always divisible by 1. So it is bound to reduce to 0. That is why we move it by 2 steps and move it by 1 step. So that the difference is 1. We can move it by 3 as well. But in that case, the difference will not be 1. And you might not reach 0. Because the difference in distance is 1. It's bound to reach 0. And this is the intuition. So that was about the proof that why will they collide. And I hope you've understood the intuition behind moving the slow by 1 and the fast by 2. Because you want to keep the difference as 1. So that they collide. Got it? So I hope you've understood the intuition and the proof. And you can watch out most of the YouTube videos. What they do is, this moves by 1 step. This moves by 2 step. And whenever they collide, we return true. That's it. They will never tell you, why are we moving it by 1? Why are we moving it by 2? Why? They will never tell you that. Trust me. And this is the reason I'm telling you, please do watch my videos, because I'll not be just cramming you up algorithms. I'll be telling you about the thought process so that you can solve new problems as well. I'll be teaching you real problem solving over here. So what will be the time complexity? It will be somewhere around big of n. I cannot pinpoint that this is the time complexity, because depending on different test cases, it might vary. You might just find it at the earliest step, you might find it at the end, you might find it at the middle, right? What about the space complexity? We're not using any external space. We're using just the slow pointer and the fast pointer. So that is about the time complexity and the space complexity. So let's quickly get back into the code editor. As you can see, we need to return a boolean stating if there is a loop or there is no loop. You have to complete the function detect cycle, and you're given the head of the linked list. And we write the exact same code, and I'll quickly go ahead and submit this. And as I submit, it will run. It does. So what I do is I'll go to Java now, and I'll copy paste the same code, the same function definition. What I'll do is I'll remove the pointers, because in Java there is no concept of pointers. And I'll make this in lower caps. And after this, I'll make it dot. This one as dot. If you see, the logic stays the same. The logic is same. It is just the concept of the pointers that changes in Java, and if I submit this code, it will be running as well. So I hope you've understood everything, specifically the intuition part, and in case you did, please do consider giving us a like, and if you are new to our channel, do consider subscribing to us as well. With this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye bye, take care.
Whenever your heart is broken